This video is going to be about a concept called Hardy-Weinberg Equilibrium, which is a way of using formulas that are used to calculate allele frequencies, which I mentioned in the population evolution video. Now, to use the formula, Hardy-Weinberg assumes the population isn't evolving, which means it must follow these 5 rules. The 5 rules of Hardy-Weinberg equilibrium are going to be no natural selection can happen, no mutations, no sexual selection, no genetic drift, and no gene flow, since all of those things cause allele frequency change and thus evolution. Hardy-Weinberg assumes that the population is not evolving. These 5 rules have come up on the AP exam, so just make sure that you commit them to memory, because if any of these 5 things are not happening, so if natural selection is occurring, if there is a mutation, then that population is no longer going to be in what's considered Hardy-Weinberg equilibrium, and the formulas I'm about to introduce will not be usable. Essentially, to summarize, if allele frequencies are changing from one generation to the next, then evolution is happening. And if allele frequencies do not change from one generation to the next, then evolution is not occurring and the population is considered in equilibrium. So now let's move on to the actual Hardy-Weinberg equations. So how do we calculate allele frequency, or the percentages of alleles? So the first equation is going to be P plus Q equals 1, where P is equal to the total number of dominant alleles in a population, and Q is equal to the total number of recessive alleles. One thing you need to remember is that P and Q always equal 1, or 100% of the alleles in the population, because if you look at a population, the alleles are either going to be dominant or recessive. We're going to assume this is classic Mendelian genetics and there isn't some sort of multiple allele situation. We're just going to say that it's clear-cut dominant recessive alleles. So they're always going to equal 100%. Now, in Hardy-Weinberg, there's actually another equation that is used to find the genotypes. This equation is P squared plus 2PQ plus Q squared equals 1. Now, each of these represents our 3 genotypes that we've talked about in genetics, the first being homozygous dominant. So P squared is going to be equal to the percentage of homozygous dominant individuals in a population. 2PQ is going to be equal to the heterozygous individuals, because they have a P, or a 1 dominant allele, and a Q, 1 recessive allele. And Q squared is going to be representative of the homozygous recessive individuals. Again, because these are the only genotype possibilities, if you add them all together, you're going to get 100% of the population. Now, the reason why this equation has 2 aspects to it, P and Q, is because there's really just a dominant and a recessive allele. But why we have 3 here is because there are 3 genotypes. You have the homozygous dominant heterozygous, which is a mixture of the dominant and recessive alleles, and then you have your homozygous recessive. So what I want to do now is let's get to an example of how we can use these formulas to figure out what the allele frequency percentages are of a population. So let's say that this is our population of bugs, and that green is dominant and black is recessive. Now, the first thing with Hardy-Weinberg to notice is going to be the recessive individuals. The reason why that's important is because if you are dominant looking, I can't tell what your genotype is based on appearance, because you could be either homozygous dominant or heterozygous. However, with our recessive individuals, we know that their genotype has to be homozygous recessive. However, the genotype of our green guys are going to be sort of a mystery, and we can use the formulas to guesstimate how many of those are probably homozygous dominant and heterozygous, but the only thing we know for sure right now is that 4 of our 10 bugs are homozygous recessive. So a good rule of thumb when you're solving Hardy-Weinberg problems is to always start with Q squared. Q squared being the percentage of the individuals and the amount of alleles that are in the homozygous recessive population. So we're going to start with Q squared. Q squared is going to be equal to the number of recessive individuals divided by the total population. So in this case, our Q squared is going to be equal to 4 out of 10 because we have 4 recessive individuals out of 10 bugs. That's going to give us 4 out of 10 or 0.4. Now the 0.4 is what I'm going to use for the rest of the video. I'm going to use the fractions, the decimal, just because it makes it easier when we're working our numbers. So the next thing we want to do is find Q. So if we know that Q squared is equal to 0.4, that means that in order to find Q, we just need to take the square root of Q squared, whatever that is for the population you're working with, and that gives you Q, which in this case is going to be 0.63. If you remember our formula from earlier, the equation is P plus Q equals 1. So if we know that Q is 0.63, the next step is going to be taking 1 minus 0.63 to find P, or rearranging that formula from earlier. So here you can see that I've rearranged the formula from earlier to where we can find P if we know what Q is. Well, we know that Q from the last sort of step is 0.63. So we're just going to plug that into Q here. And that means that P in this case is going to be equal to 0.37. Once you know what P is, you can find any of the other genotypes, meaning the equation that is P squared plus 2PQ plus Q squared equals 1. If I asked you, well, what's the percentage of the homozygous dominant population? What you would do is use the P squared from this formula, and that never changes. P squared is always equal to the homozygous dominant population. So like, what percent are homozygous dominant? Well, at this point, if you found Q and you found P, you can do anything. So all we have to do is to find the homozygous dominant population percentage. We're just going to plug in 0.37 for P. So if we square 0.37, what we get is P squared is equal to 0.14, or about 14% of the population is homozygous recessive. That's what that represents. So lastly, we can figure out, well, what percentage of the population is heterozygous? Well, that's going to be from our genotype formula, 2PQ. Again, at this point, it's just plug and chug once you know what P and Q are. So if 2PQ is what we need to use, we just do 2 times P, which is 0.37, times Q, which was 0.63. You just plug that into a calculator, and what we get is the 2PQ value, or the heterozygous percentage, is going to be about 47%, or we get 0.47. And that is how you're going to solve Hardy-Weinberg problems. You always find Q squared by looking at the population. It's always equal to the number of recessive individuals divided by the total. And then from there you can find Q, P, and then it's just plug and chug. So I think we should do one more example just to see this in action before you try some problems on your own. So if you get a problem where it tells you 16% of a population of 100 are recessive and can taste the PTC, paper bitterness, how many individuals are heterozygous? So in this case, it's already told us that the homozygous recessive population is 16%. So remember, the homozygous recessive population is equal to Q squared from our formula, and that's going to be 0.16 or 16%. So remember, the formula is going to be P squared plus 2PQ plus Q squared equals 1. Right now, it's asking us about the heterozygous individual, so we're looking for 2PQ in particular for this problem. Now, if they ask for the homozygous dominant individual, you would use P squared. So now we have Q squared. Let's find Q. Q is going to be equal to the square root of Q squared. So in this case, we're going to have Q is equal to 0.4. And with our other formula, P plus Q equals 1, we just plug the 0.4 in for Q, and that means that 1 minus 0.4, which is just Q, I'm just rearranging this formula, is equal to P. So that means P must be equal to 0.6. So now that we have our Q value and our P value here, we can plug that in for the heterozygous, and if the heterozygous is equal to 2 times P times Q, in this case, we're going to plug that in, and what we get when you plug that into the calculator is going to be about 48%. So I'm asking how many individuals are heterozygous. In this case, it's easy because it's a population of 100, so you would just multiply that total by 48%. So in this case, it's just 48 individuals would be heterozygous. But if the population was like 246, the only difference is you would just plug that value in here to get the number of individuals. And that's an example of another Hardy-Weinberg problem that you might have to solve. So do your best on these problems. Always try to find Q first. Sometimes the problems are more simple and they just flat out tell you, you know, Q is equal to 0.55, which means that, you know, you could just instantly subtract that minus 1 to get P. You can kind of just take whatever information they provide you and use it, and just remember what the letters P, Q, P squared, 2PQ, and Q squared represent, and you'll be fine.